Thank you very much. Thank you all for having me. So this talk is going to be about Vtune, the way I use it. I'm not going to teach you everything there is to know about Vtune, but I'm going to teach you the important things about Vtune, or at least the ways to find out what the important things are, and hopefully whet your interest going forward. However, I thought I'd stop, and I'll do this quite quickly. I do want to talk just a bit about Knights Landing architecture, just because I think it's useful to have a framework. I'm programming to something that looks like this. You know, here's where data comes in, here's where it goes out, here's where it's computed on. You'll have a mental picture of where the bottlenecks are and where you need to look for performance. So I will not spend a ton of time on this slide. I'll just let you read it as it builds. But this is the microprocessor that is in Theta. And this talk is specifically targeted for Knights Landing, but almost everything I say is applicable either verbatim or with minor variations to any Intel architecture processor, not just Knights Landing. The important things here are things like the, let's see, 2 VPUs, so you want to keep them both busy. High bandwidth memory, but a small amount of it. Lower bandwidth memory, but more of it. For MPI codes, the network connection, whether it's on processor, off processor, doesn't really make any difference. It's going through PCI, so there's another bottleneck to look at. The rest of this is just kind of fluff, except there's a lot of cores, and they are relatively slow cores. So that turns out to be important. These are the features of the Knights Landing core. One distinction from Xeon, it's got 4 threads per core versus 2. You don't have to use them all. In fact, often you don't want to use them all, but you can use them all. It's got modest out of order, a lot of floating point. One interesting thing to note here is that it can only retire 2 instructions per cycle. In order to use both floating point units, that requires 2 instructions. So that means if you are running at full speed, retiring 2 VPU ops every cycle, then you can't be retiring any other instructions. For example, branches and loop counters and stuff like that. So you will never get 2x AVX 512 every cycle because you can't retire enough instructions to do it. So there's a big difference between theoretical maximum performance and achievable performance, and it's important to be aware of that so you know when you're done. This is my simplified working model of throughput analysis and performance. As I said, the peak so I assume everybody here is concerned with flops or with at least doing SIMD types of operations, so working on 512-bit vectors, doing floating point or doing integer operations, but doing that vectorized chunk at a time. The fastest possible throughput you can get on KNL is when you're doing 2 of those every cycle, right? If you are not doing 2 of those every cycle, then you would like to know why. There's lots of reasons. I'm kind of getting ahead of myself. So first of all, I want to retire 2 SIMD instructions per cycle to get throughput. I want those SIMD instructions to use all of the lanes. So I want them to be doing 16 single precision or 8 double precision operations per SIMD operation per cycle. So that means I have to vectorize. I also have to parallelize because I have to use all the cores, all the SIMD units on all the cores. I may not be able to get there, and this gets back to what James was mentioning earlier about roofline. I just think of it as bottlenecks, right? There's some limiting factor. Once you remove that limiting factor, there's another limiting factor, and so on until you're at the peak of all the limiting factors, or else know why you're not. So memory bandwidth is certainly the biggest thing in HPC. There are lots of other reasons you might not get full throughput, but memory bandwidth is almost always the first and foremost one in HPC codes. So that's my goal, is peak throughput. getting there is what I'm calling performance optimization. Knowing why I'm not there yet is performance analysis. And what I'm going to talk about today is using Vtune to analyze the performance of your machine to try to find out why you are not getting peak performance, or if you are getting peak performance, what's the bottleneck that's your roof line, and how close are you to it? And I don't cover every possible thing there, but hopefully I give you enough idea to realize what you can do with the tool. Again, there are reasons I may not be able to retire 2 fully packed SIMD operations per clock. My algorithm, okay, so again, you've got to have, there's 2 levels of performance. There's parallelism, using all the cores, and even another level above that, using all the nodes in Theta, for example. So MPI parallelism, threaded parallelism, or that could also be MPI on-node parallelism. And then there's core performance, which is, in this particular case, SIMD users. So first, talking about parallel scalability, there's AMDAL comes in. If you've got synchronization, and if you've got load imbalance, where some nodes or ranks or threads are doing more work than others. In the extreme case, serial code is the extreme case of load imbalance, where one thread is doing, or one thread per node is doing 100% of the work, and all the other threads are doing 0% of the work. Arguably, those are algorithmic problems. I'm doing a CG solver, so my algorithm says I need a global norm every time step. That means I have to do an all-to-all reduction every time step. So a big all reduce. And that's going to mean that I've got a barrier every time step. And so I've got this serialization point, which is going to limit my scalability. If I had a different algorithm that didn't require global communication, my code would probably be more scalable. Architectural reasons for imperfect scalability are either I'm using all the resources of the machine, or I've got some kind of a conflict on some resources that's bottlenecking me. So James mentioned cache. If I'm only using a quarter of the cache because of bad memory alignment, then that will prevent me from, that will cause my machine to stall, which will prevent me from doing useful work with all the machine cycles. If I'm memory bandwidth limited, there may be nothing I can do about that. If I'm using all the memory bandwidth of the machine and my algorithm requires that I use all the memory bandwidth, then that's my roof line, and I'm happy and I'm done. Or I come up with a new algorithm that isn't bandwidth. So that's, architectural for a given algorithm. Changing the algorithm changes the game completely, and you have to start over. I already talked about interconnect. There's on-chip interconnect between the cores, and there's off-chip interconnect, the fabric, which is MPI. And then for SIMD, the big trick on Intel architecture is getting your code to vectorize. And often the compiler can do it. When it can't, you can rewrite your code so that the compiler can do it, and in the limit, you can write it in intrinsics or assembly language. Again, this talk is really not about performance optimization, but I want you to know what you're aiming towards, because ultimately you'll use the tool, you'll find some bottlenecks, and then you'll look at this and say, oh, I need to change my code, I need to vectorize, so on and so forth. Okay, so how do I use Vtune to find these impediments? This is how I use Vtune. Vtune has a lot of features. I don't think you need to use them all. I'm hoping you'll find these to be useful. I recommend that you only use the hardware event types, and I have a list at the very end about the event types, the actual collection types that I recommend that you use. Again, I want you to think in terms of a simple model of the machine. So threads execute code. A thread can be an OpenMP thread. It can be you can run one MPI rank with no OpenMP threading at all, in which case a thread is just a single process. It doesn't really matter. As far as I'm concerned, a thread is an execution unit. It's something that runs code. Code is code, but it's useful to think about it, bucket it into conceptual or physical modules. So the most convenient use that works really well is shared objects. So I know if my code is executing in libmpi.so, that it's doing MPI. I know if my code is in libiamp5.so that it's doing OpenMP, right? I know if my code is in my application, foobar, that it's doing foobar. And then I can break that down. I say if it's in a function in my app that's doing an FFT, then it's doing an FFT. So you can imagine. So the idea is you bucket your code into meaningful units. You have threads that execute code. And to get back to what I said at the beginning, there's parallelism and then there's per core. How well is the core doing? When you compare the way code segments are executing across threads, that tells you about parallelism. And when you look at a single thread and different code segments and how well they're doing relative to peak performance, that's per core parallelism. So everything else in this presentation refers back to these models. Okay, so now the rest of the talk, I'm going to slow down a little because this is the important stuff, is a case study. I picked MiniFE, which many of you may have heard of. It's one of the Mantivo mini apps, originally from one of the labs. I'm going to say Livermore, but I might be wrong. It's a highly optimized code. It was really a poor choice for this. You'll see in a bit that it turned out to be a really good choice. So I got lucky. I made kind of two bad things happen, and they made a good thing. So it makes the talk far more interesting than it would have been otherwise. I could have picked a bad application, but that was too much work. So I picked this one. It's nice because it's hybrid. So you can run as many MPI ranks per node as you want, up to one or more MPI ranks per node. And each of those ranks can have as many threads as you want. You would never want to have more than the total number of hardware threads in the machine, obviously, but you can mix and match them any way you want. So in this particular case, I had planned on running a multi-node run, but because of some software installation issues on Theta that are now resolved, in order to get the talk done in time, I ran on only one node. All the methods are still valid, all the data is still valid. So I ran 8 MPI ranks on one node. They were communicating through shared memory. This is Cray MPI, it's on Theta. And then these are the steps that I'll talk you through. So how to run and collect Vtune on Theta. And again, this is not a full user's guide, but it gives you enough to get started and has pointers to everything else. We'll look at what the data, kind of the first thing you see when you bring up Vtune. Then we'll go through the 2 bits I talked about, the parallel performance, and how do you analyze that. And this is where the interesting bit comes in. And then processor performance, how well is this code doing relative to what the processor actually can do. And then how do I know when I'm done? Have I hit the roof line, if you like. So this is the first bit. So let's see, and the next slide I'll tell you a little bit more. So this is kind of just mechanically follow this. So I'm going to say use hardware account. Vtune has some analyses. The other presentations didn't really go into this in detail, but there are a couple of different ways. Vtune is a sampling approach. So I'll describe exactly how that works. But it can sample based on software events or hardware events, and it also has some tracing capabilities, to use the terminology that we learned this morning. In this case, I'm only interested in the hardware counter sampling, and I'll describe exactly how that works in the next slide. In this case, I recommend, if you've got 1,024 nodes, you really don't want to look at Vtune profiles for all 1,024 nodes. And there are plenty of other tools that do better than Vtune at telling you about global behavior, like Intel Trace Analyzer Collector, which used to be called Vampire. That's the old Vampire from way back. Or the current ScoreP Vampire, or HPC Toolkit, or Tau, or Alinea Map. Any of those are fine tools, or Cray's tools as well, which I haven't used, but they come well recommended from a lot of people. We'll tell you about global behavior. What I'm saying is you pick a rank, normally rank 0, it can be any rank you want. You run Vtune on only that rank and tell it to collect on the whole node. So if you're running 64 ranks on that node, you'll see all 64 ranks, but they'll all be in one experiment. The overhead with that kind of collection is very, very low with Vtune. That's one of the huge advantages of Vtune over Linux perf. Anything that's based on PAPI, for example, that uses interrupts, the overhead is much lower, and there's technical reasons I can discuss if people are interested. This is a recipe to do that. So I use ap-run, which is the cray/theta app run command. And I run this script, which then says, if I'm rank 0, run Vtune this way. There's a bunch of other ways to do it. This is not the only correct way to do this, but this way works. And again, this command line, if you're an expert on Theta, you'll probably say, oh, why is he using all that? I only need this and this. Fine, do it any way you want. But what this says, I know some of these are important. In particular, this says, give me all the threads. And this says I want 4 hyperthreads per node, and that lets my OpenMP runtime see the whole MPI rank, all the cores allocated to it. That's worth a whole another couple of slides in itself, but I don't go into that. 8 ranks with 8 ranks per node, and then I run this shell script. And the 32 there says give me 32 threads per rank, which with 4 threads per core works out to 8. Cores per rank, and remember I said there's 8 ranks, 64 cores, 64 cores. Okay, so I've done that. I should call this out a little more. This finalization mode equals none. After Vtune has collected all the samples, it needs to do a post-processing step to resolve those together with the symbolic information that's contained in your executable and in the shared objects. That's a fairly expensive process, and it's very, very slow on the compute nodes because of this. It's a serial process, and it's running on 1 core of KNL, which is much slower than 1 core of the login node. So if you just tell it, don't do that until, defer that until later. So that's what this does. Otherwise, your job will sit there, it'll be running on 1 node doing nothing but 1 core worth of thing, locking down the whole system. So you're much better off doing that. Collect advanced spots is the hardware counter default. Analyze system has analyzed the whole system. And then these are just the command line for the application itself. Okay, I'm done with that. Now I switch back to Theta Mom or whatever. Source or module load Vtune, either of those works. And then I tell it to finalize, and I say, look here for the object files. So that's an important step because otherwise it won't know your function names. You'll just see, oh, it was in my executable, but you won't know which function or anything. You may also want to see symbols that are in shared libraries or other libraries, in which case you also need to add the paths to those. And it will tell you what it can't find when it's trying to finalize, and then you can see if any of those look like stuff you wanted to go back and fix. And then you run the GUI. And we were just doing a little work at TAC, hands-on before lunch. I don't know how hard this is to do. I haven't figured out how to do this on Argonne, so you need to talk to somebody at Argonne. Or you can put the GUI on your Mac and download the file, but you need a license and all of that. So for now, if you'll pardon me, I'll just assume you have a way to run the GUI, and then if you don't, we'll try to figure that out later during the hands-on. I don't expect you to be able to see this. This is really, but I want you to get a feel for what you would see when it came up. And there's a few things that I'll talk a lot about grouping. So that's right here at the top. You can click there and change the grouping of the results by the code segment. Remember I talked about code segments, so modules, functions, loops, addresses, all sorts of things. In this case, it's by module at the top. This is the timeline, this is the grid, and this is the viewpoint. So those, and then there's some little fiddly things down here that can be fun to play with. But this is just really an orientation sort of a photo. This is, now the rest of the presentation will have little snippets pulled out, screenshots pulled out of that, and then I'll try to describe as I go through what happened. So the first thing I did is I ran Vtune. I got that picture you just saw. One thing to note on Cray systems, by default, the Cray wrappers link things statically, which makes it much harder to figure out which bits are MPI and which bits are OpenMP and which bits are FFTs and so forth. And so if you link instead dynamically, which is not the default, then you kind of automatically get this bucketing I was talking about. And so here, MiniFE is the name of the application. That's normally what you would think of when you compile and link your application. You get a.out. That's a.out. This is the shared object for OpenMP. This is the kernel, VM Linux. libimpitch, this is Cray's MPI runtime, standard C, Intel C, libc, that's probably a printf or something. More MPI, so there's a couple of MPI, or PMI, but it's probably part of MPI, and then another standard C. So by virtue of the fact that these chunks of code are already in these shared objects, you get this bucketing effect for free, which is really useful when you're trying to figure out why a thread is spending a bunch of time in OpenMP, for example. And then this is the timeline, the point at the bottom. While this is a sampling-based tool, it saves all the samples. So it does not accumulate a profile on the fly, which is the impression I got from some of the talks this morning, that since their data files are so small, they must be accumulating things on the fly. Vtune actually saves the whole thing. So this gets bigger the longer you run. But it means you actually do get, even though it's sampling, each of these is a discrete event, you get all the events over time. And in particular, this code in MiniFE, the initialization is not threaded. And so only one node, if you saw the full timeline, you see that only 8 threads are actually doing anything, and the other 8 are sitting in OpenMP, but the important point I'm trying to make here is that I don't really care about any of this. This is all initialization, right? What I really care about is the kernel. And so be careful. If you just run Vtune without paying any attention, you could end up spending a bunch of time optimizing stuff that you don't care about. You can pause or resume sampling, or you can zoom in on the timeline. In the rest of these examples, I actually zoomed in on the timeline to do that. Okay, I thought this slide was earlier, but so I keep saying it's on the next slide, but it's here. This is how Vtune actually works with the hardware sampling modes. Collect advanced hotspots, for example. There's 3 fixed counters on every Intel architecture machines, fixed frequency cycles, actual frequency cycles, and number of instructions retired. So each of those each of those counters is programmed to interrupt after a certain number of events have occurred. The approximate frequency is 100 hertz, roughly, so it's pretty granular. It's like 13 million instructions at 13 million clocks at 1.3 gigahertz. So a lot of things go on between samples. So it is a statistical sampling. And then each of those saves with it, I think James mentioned this morning, the instruction pointer, and that's how I know which module I'm in, for example. The thread ID, the Linux thread ID, the actual hardware thread on which it was running, which I'll talk about that more a little bit. And you can also get the call stack optionally, although I rarely use that. And for all of what I'm talking about today, call stack is really useful in understanding program behavior, but once you understand your program behavior, it's not all that useful. I don't use it day to day. It doesn't help me with optimization usually, except at a very high level. And from these, you can compute all sorts of interesting metrics just from these 3 events. I can tell you what my relative frequency is versus my actual frequency. So Intel processors speed up and slow down depending on power and how many cores are active and what instruction mix is getting executed. So I've got one tick that always ticks at 1.3, 1.4 gigahertz, and then another tick that ticks at the actual. So at any point in time, I can tell you what the turbo frequency is, which determines the actual elapsed time. I can also tell you how many instructions per cycle are being executed. And that's really if you like, the only thing you need to know about how well your core is doing. That's a simplification. But it's the single most important number to tell you how well your core is doing is how many instructions per cycle are being executed. One nice thing about Vtune is that it's very, very low overhead because the interrupts don't propagate back to the user program. And so compared to any of the other ways of collecting this data, if you use advanced hotspots with a reasonable sample after value, so you're getting a interrupt frequency of between 100 and 1,000 hertz, then your overhead should be 3% or less. And so it's really, really nice for that. Remember I said you don't need data for MPI? No, there's a lot of data here. It's hard enough to go through one, especially when you consider there might be 64 or 128 threads. Multiply that by 64 nodes, and you've already got too much data. And collect only the interesting bits. So I kind of said all of this stuff already, so this is just a reminder. Okay, so I've done that. I brought up Vtune. I zeroed in on the bit I was talking about here. And then so now what I wanted to know is, why am I spending so much time in libiomp5, right? Remember, if you go back and look at this top thing here, I've got this huge amount of time in libiomp5. OpenMP can't be that slow, right? Well, it's not. What it's really doing is waiting. So in other words, all the threads have hit a barrier except for one. And so all of the threads that are at that barrier, either waiting to end a parallel region or waiting to begin a new parallel region, are doing nothing useful. And that shows up as OpenMP time. My object here was to try to explain that. And in fact, I happen to know that this code does MPI, and I know that, like most codes, MPI is done in a single-threaded region. So while one thread is doing MPI, all of the other threads in that MPI rank are spinning in OpenMP. They're essentially not, they're outside of a parallel region. And so I wanted to test that hypothesis. So I went in and if you run Vtune properly, these threads should have names like master thread and slave thread. I didn't quite run it right, and so I picked these based on looking at which ones I knew spent time in MPI, so I cheated a little bit. I'll show you a way to not cheat on the next slide. But so I picked one master thread, which I knew was doing MPI, and one slave thread, which I knew wasn't doing MPI. And I selected them both, and then I filtered in. So filtering is incredibly powerful. I filtered in by those, and then I switched my viewpoint. So now I've got modules on top. And then I just expand one level. So I see that okay, 408.01 and 411.03 are both spending almost exactly the same amount of time and almost exactly the same number of instructions in mini-FE, which remember is my application. But 411.03 is spending, almost 3 times 10 to the 9th clock ticks in OpenMP, whereas this one, the other thread, is spending only 182 times 10 to the 6th. But that time's made up for in MPI. So, first question is, does my MPI time, and the other thing to note here is that these numbers here are summed over all of the threads. But these numbers here, because of the way I selected and grouped in, are per thread. So you can imagine, if you take, right here, this tells me I have just proven that all of my OpenMP time is due to MPI time. But if you take the total number, this is only going to get multiplied by 8, right, the MPI time, because there's only 8 MPI ranks. This is going to get multiplied by 7 times 8, 56, because there's 56 OpenMP threads. So this number looks much huger than it is. And it's important to look at per thread time and then compare those threads together, because the longest per thread time determines the elapsed time in a both synchronous program, which almost always HPC programs are. They have MPI message passing, or they have OpenMP barriers that cause synchronization points, which makes the slowest thread the worst. And so speeding up the fastest thread does you no good. Finding the slowest thread and speeding it up does you a lot of good, even though it won't change the numbers that much, or some of the numbers. So this is how I did it, and I may have time to zip through this real quick. We'll see how fast I go. So great, we're done, right? Well, I only looked at 2 threads, and really, to be honest, I should look at all of them. That's kind of hard to do in Vtune. You can imagine this display doesn't scale all that well when I've got 64, and then I'm trying to compare something that's up here with something that's way down here. Kind of got ahead of myself. Right, okay, so this is describing, so here's what we did. We did kind of the first few bullets here. We determined our elapsed time by we looked at the longest executing threads, and we determined that spin weight in OpenMP is equal to MPI time. But we also know that there's other sources of load imbalance, like MPI spin weighting. So we can look at every thread in every module and compare them. But that's really hard to do in the Vtune GUI because of it's all one big line, and you have to scroll up and down. So instead, what you can do is a pivot table. So any of you who have done any spreadsheeting know what a pivot table is. You essentially take threads on one side. You take one thing on one side, one thing in the rows, one thing across the top, and anything that's the same in both you add together. So, I have a way to generate that and import it into Vtune, or import it into Excel, which is what I'll show you here. But I also use Python and Pandas, and I'm hoping to make all this stuff public in the next couple of months. It's just a matter of getting it prettied up. But this is what you end up with. So this is just a cut and a paste from a spreadsheet pivot table. So what I've got here, and I deleted the middle of it because it's all the same. So this is 64 threads. Okay, I built a pivot table. So this is the time those threads spin in mini-FE, libiamp5, libmpitch. These were the top 4. So I took all the others, and I sorted that way. I sorted this first by time in MPI. So you can see I got these were the only ones with any time in MPI. And then I sorted again by OpenMP time. You can see these all have, the top ones, the top MPI threads all have very small OpenMP time. The bottom ones have about equal OpenMP time. And remember, there's a big, I should have drawn a little tear or something, but it's right around in here. There's another 49 threads or something like that. But what happened here, right? So this is why this was a bad example, because actually these all should have been this number here. They should have all been 78,000. But for some reason, because this is incredibly well-balanced app, so I would have been done. I say, see how well-balanced this is? Now go make your app look like this, and I'm done, right? That's not very interesting. Well, it turns out that I found this problem. And it's like, well, what the heck? So for some reason, master thread 0 is taking about 20% longer in the application than all the other threads. So I will, in the interest of time, I'm going to go over this. But what I ended up doing was finding 2 master threads here and comparing them. So this is similar to the comparison I showed you, but a different grouping. So I just sit here all day, honestly. I sit here all day and do this with Vtune. And then when I don't like the display, I put it into a spreadsheet or I write some Python. But you can see, okay, so this is basically all the stuff that's running on CPU 0, including stuff that isn't part of my app. Remember, the whole operating system's out there doing stuff. So this is all this other stuff. What are these DVSs? And most of this looks like it's from my app. Vtune tells you like this. This is from Vtune here. This is all from its app. But really, there's not much stuff. And you can see right here that in mini-FE, CPU 8 spent 7.4 E9 instructions, 7.3. So why the heck? But this is 13, and this is 10. So again, I have no idea why. And then I remember I told you there's 4 threads per core? Linux sees those all as OS CPUs. So I said, well, let's look at let's look at the core instead of the threads. And lo and behold, CPU 64, which is the second hyperthread on core 0, is executing 1.1 E9 instructions while my program is running. But only on CPU 0, right? All the other ones were about the same. But that's causing, since those are on the same core, they're using the same resources, even though the OS thinks they're separate, they're not. It's slowing this one down. So, so this is a perfectly balanced app. And it should be running 20% faster, but it's not because something is running on the system that's slowing it down. And I found that with Vtune, and I completely did not expect this. So anyway, I thought that was pretty cool. I am going to speed up a little bit. I think I've covered all of this. Yes, I have. So this is just, and there's a ton of other things you can do with pivot tables. Like I said, that previous one, if I had been doing automatic things and said, for example, look at other things running on this core and see if they're part of my process, simple things like that, I would have seen that right away. And I wouldn't have had to go through all of that. So Vtune has lots of data, but we're still working on coming out with good summary reports that prevent, this, like the version of sending it to the cloud and having it tell you that this, having automated analysis that you can just look at it and immediately spot, oh, this is wrong, and figure out why. Now I'm going to turn real quickly in the few minutes we have left to the core performance. The key measure of how fast a core is going is how many instructions per cycle it's executing. This is one of my pet peeves, is that as you just saw, if you're running 2 threads per core, each thread is running slower, right? We just saw that happen by accident. Well, if you can be doing it, and there's reasons to do it in reality, you can hide cache misses and things like that. But your CPI changes. Vtune always supports CPI per thread, but you really want CPI per core. So essentially, you can either divide or multiply by the number of active threads, not 4, right? If you're only running 1 thread, you multiply by 1 or divide by 1. If you're running 2, and so forth. But however many, and you only, Vtune can figure that out for you, but it doesn't automatically. You have to look at it. And when you're doing your scaling graphs, please don't show me 1 to 64 and then 64 to 128 on the same timeline, because it doesn't mean anything. You could be running 3 threads on 1 core, 4 threads on 1 core, 2 threads on, show me 1 thread per core, 2 threads per core, 4 threads per core. And the x-axis is always cores. The y-axis is whatever you want, speed up or efficiency. Huge pet peeve of mine, meaningless graph, don't do it. How do we figure out CPI? James talked a lot about top-down analysis, stall cycles. Vtune will do that for you semi-automatically. I think it's very useful. The other way to do it is to, in this particular case I knew, but in HPC codes I normally assume that it's memory. And so I look at some specific things first, but you can do it in any order you want. But I'm walking you through this because it's actually showing you things that Vtune can do that are much harder to do with other tools. I specifically said I want to collect, so these 3 counters I mentioned before, and 13, this is about 100 hertz. I've also added these other 2. So I'm going to look at L2 misses, I'm going to look at these specific hardware events. Together, those 2 hardware events add up to the number of cache lines coming into L2. And so I can compute an L2 input read bandwidth per cycle, which is on KNL exactly analogous to memory bandwidth, memory read bandwidth, because there's no L3. And so this is just, I sliced a Vtune thing. This is what you get. These are interesting here at the top, because these are actually, and you can really see the only one we really care about is this top one, but I included these other 2 for fun. So spending all its time in these 3 functions, and here's some numbers. What do these numbers mean? Well, I put it into a spreadsheet, and I do this calculation. And as I said, these are the number of lines in. You multiply by 64 to get the bytes. You can determine elapsed cycles by reference clocks, which is the sum of the cycles over all the threads divided by however many active threads there were. In this case, 1 thread per core. So divide that by 64. And then multiply it to get the gigahertz, 2.3. And I can see that I'm getting 260, my peak is around 350. So these two loops are pretty close to peak. So these two are near the roof line. I think they're fine. I probably don't have to worry about them. This one, could it be any better? I don't know. So now, the part you've all been waiting for, go to the assembly code. And we can see this one's bad because it's got a getter. But this one's good because it's all contiguous. And so it's just basically string. There's some other metrics you can use by exploring the Vtune. And then, how do you know when you've done? I've hit a roof line, you know. But I want to make sure I really, really needed to hit that roof line. In other words, if I'm reading the same data 14 times, I may be using all the bandwidth. But what if I could only read it once, right? So you got to make sure you've got a sensible algorithm that's tiled and doing the minimum, you know, absolute minimum computation, minimum bandwidth, and then have I hit a roof line? Have I hit a limiter somewhere in the network, in the memory, or in the core? And if I have, I'm happy. If I'm not, you know, in other words, I've got the best realization of this program for my code. If I can prove that, if I don't, then I either go improve my code or I change my algorithm. So that's it.
Hey Larry, thank you for a great presentation. It was very interesting. We're kind of, at least I missed the details of a point you made there towards the end. We just turned something into supercomputing a couple of weeks ago, and we violated your pet peeve that you mentioned a couple of minutes ago about plotting, scaling plots out to the number of threads, whereas you said, I think you said you wanted the actual hardware on the x-axis.
No, what I want...
You said there again?
Yeah, sorry. So I should have drawn a picture. I've actually got an XKCD that I'm trying to make even funnier, and then I'll publish it. But essentially, I want cores on the x-axis, not threads, right? So on Theta, that should go from 0 to 63, or sorry, 1 to 64. And I want your figure of merit on the y-axis. That's up to you. And then I want 3 lines. I want 1 thread per core, 2 threads per core, and 4 threads per core.
The reason was you said we could have a thread here, 2 threads here.
Right. I mean, you would never want to do that. But when you tell me you've run 64 threads, I don't know if you've run 32 cores with 2 threads per core or 64 cores with 1 thread. And that one's kind of obvious if you're always using all the cores. You know, if you're always using all the cores, it's okay. But then why are you plotting it in the first place? So, yeah, so it's just because it really makes a difference how many threads per core you are running. It's a useful bit of information, and when you just plot from 0 to 256, you know, you get these weird graphs, and you don't know why. So, sure. Okay.
When you were talking about, you said you had an example and you were saying like I don't want to really start like my analyzing until after the initialization just because like I don't care in this example.
Right.
So I was wondering how in general you might do that, especially if you know that like if for example you only care about looking at code in some particular kernel, like how you might filter that based on or given that you're like sampling so that you don't necessarily like you can't like maybe set a like you can't say manually like call the sample every time you enter a certain function. Like yeah, I was wondering. I don't know, like how.
Well, you can. So okay, so if you're concerned about a loop, for example, then you know if you are executing that loop enough times to be statistically valid, then you can just filter in Vtune. So you can just you know, go to that loop and select it, and it will show you the important metrics. If you've got something with more sort of time-oriented phases, like you've got initialization, and then you've got time steps. And let's say you're normally doing 1,000 time steps, but after time step 3, they're all the same. Then you can just say, if I equals 3, start sampling, and then if I equals 12, stop sampling, right, in your code. And then you can, and then within that, you may want to play around, but that makes the data volume manageable. So you kind of you can both pre-filter and post-filter. But it is sampling. I didn't, I could have a whole nother talk about tracing versus sampling, and I love tracing, but I almost always do it by hand myself because I don't trust any tool to do it without completely changing the behavior of my program. And I'm probably overly paranoid, but anyway.
A basic KNL question.
Yeah.
But so the program that you were optimizing, it had an issue with the OS running on one of the cores.
Right.
So if you're only running on 64 cores on one of these 68 core KNLs,
Then you'd be okay.
okay, so you can.
So
you can
my
trust that the
recommendation is if you're on a 68-core system, you always avoid 0 and 1, which is tile 0, because they share an L2. And that gives you 66 cores. Unfortunately, Theta only has 64, and so it's kind of hard to, in most cases. You could try avoiding 0 if you had an OpenMP app that, had really long loops, then 63 and 64 should be fine, right? But if it's MPI and you need, 8 ranks per, and you can use 7 cores instead of 8, then. So, question?
Yeah, I guess could you just reiterate what you said at the beginning about you can only retire 2 per cycle, and that is why you can't really extract all the performance out of both?
It makes it much harder. So imagine you're doing matrix multiply, right? So all you're doing is FMAs. You can do 2 per cycle up to some number, but then you've got a branch, right? Or you've got a loop. So even if you do 16 in a row, so that's your minimum would be kind of 1 loop and 1 branch every 32 instructions. But of course it's worse than that because there's other things you have to do. So that's so that's why one of the reasons DGM, gets whatever it is, 80% or 75% of peak. And typically Xeon gets a higher percentage of peak.
80% is that's like a good.
I think 80%. I'd have to do the math, but I think 80. See, SGIM's a little better, so maybe SGIM is 85 and DGIM is 80. If you're getting 80, I'd be very happy. If you've got CFD code, of course, you're going to get 3% no matter what you do. So, but then if you're maxing memory bandwidth, arguably you are getting 80%, right? You're getting 80% of the bandwidth. You just can't get the flops. There's just no way to get them because you can't get the memory there fast enough.